Welcome to qnawire.
So let's first draw the free body diagram of the cylindrical hoop. So let's say this is our hoop and it has a radius r and mass m. So there will be a gravitational force mg acting from the center of gravity of the loop, which is the center of the loop, and there will also be a tension acting upward from the string. So this, let's call it Ft, and the radius of the hoop is given to be capital R. Now because the hoop is rolling without slipping, the acceleration of the center of mass is related to the angular acceleration by alpha times R. Now from the free body diagram, we can write Newton's second law for the vertical direction and for rotation. So Newton's law says that the net force is equal to mass times acceleration, where this is the acceleration of the center of mass, and we are solving for the vertical motion. So this will then be equal to mg minus the tension force, which is acting opposite to the gravity, and we are assuming the acceleration or the hoop moves downward. That's why we took mg to be positive and Ft, the tension force, to be negative. Now we write Newton's second law for rotation. So this will be equal to net torque, which is given by I times alpha. So this equation right here and these two are analogous for translational motion and for rotational motion. And over here, net torque is around net torque with respect to this axis passing through the center of the cylindrical hoop will be equal to Ft times R. So assuming clockwise to be positive, and since the mass of the gravitational force passes through the axis of rotation, the torque because of this force will be zero. Now we will use expression for I and R. I is the the moment of inertia of the cylindrical hoop. Now since the hoop is hollow, the moment of inertia will just be equal to mr square. If it was solid, then it would have been half mr square. But here the hoop is hollow, therefore this will just be equal to mr square. Now alpha will be center of mass acceleration at center of mass, acceleration of the center of mass over the radius of the hoop. Now we simplify this equation a little bit, so we get FTR to be equal to mass times R times acceleration of the center of mass. Now from here we get, so this radius and the radius on this side cancel out, so we get Ft to be equal to mass times acceleration of the center of mass. Now we have two equations, this one and this one. So we can use this expression of tension in this equation. So we get mg minus MACM, which is the tension force, to be equal to mass times acceleration of the center of mass. And from here we can find ACM to be equal to, so the mass on each side cancel out and we get twice of ACM to be equal to G, and therefore ACM is G over 2. Now we use this equation again in place of acceleration of the center of mass. So alpha times R is G over 2. Therefore alpha will be equal to G over 2R. Therefore the torque, the net torque, which is given by I times alpha, will be equal to mr square, which is moment of inertia of the hoop, times half G over R, which is the angular acceleration that we derived here. So this is equal to mr G over 2. Now we know that torque is the rate of change of angular momentum. So we can write this to be equal to dl over dt. This means that dl is equal to mrg over 2 times dt. Therefore, L will be equal to integral over mrg over 2 dt. Now, since this expression, this term is a constant, so we can take it out of the integral. And integration over dt is just equal to t. Therefore, L will be equal to mr gt over 2. So this is the net angular momentum. Now for the second part, we have to find the tension. We already saw that from this equation over here. So let's write that first. Now we derived an expression for the acceleration of center of mass, and we found that to be g over 2. So we plug that into this equation. So F will be equal to mass times g over 2. And as you can see, since mass and g are constants, therefore the tension force is constant in time.